In problem 1, Ashley, Lexi, Marie, and Pilar decide to go on a hike and make some hot chocolate at the top. And in part A, the pot has to be hardened, so it's placed in a high temperature furnace. This question asks you how long the component should be kept in the furnace for the mass concentration of carbon 0.6 millimeters below the surface to reach 1%. The learning objectives here are transient mass transfer. So the assumptions, properties, equations are listed, and the time was 17.36 seconds. In part B, a lid was put on the pot to speed up the heating process. We can assume the lid acts as a flat plate, and there is air flowing over this flat plate. So the critical length has to be found, and then that's used to find the Reynolds number. And finally, the hydrodynamic boundary layer. This is an example of external forced convection. Moving on to part C, we were trying to find the rate of heat transfer to the water. This is an example of boiling and or condensation learning objective. The equations and solutions are listed below. Q nucleate was assumed. So basically for this problem, a whole bunch of properties were found, plugged into Q nucleate, and then to find Q boiling, it was multiplied by the surface area. In part D, the hydrodynamic and thermal entry lengths for the hot chocolate coming through a straw are found. This is an example of internal forced convection. The equations are listed there. You need the Reynolds number to find LH and LT. In part E, the rate of heat loss from the side surfaces of the pot, assuming that the side surfaces of the pot act like a flat plate, are found. This is through natural convection and radiation, so those two learning objectives. As you can see here, for natural convection, you need the Rayleigh and Grashof number, and then from that you can find the Nusselt number and find H, heat transfer coefficient, to find Q through natural convection, and then you just need the properties given to find Q radiation. In problem 2, Ashley is baking chocolate chip cookies to bring to Marie's mermaid-themed birthday party, and couldn't tell if they were done after 15 minutes, even though they were only supposed to be cooking for 7 minutes. So, what she's going to do is assume that the cookie is a short cylinder. This uses learning objectives, cylindrical coordinates, multidimensional spatial variations of heat transfer. So, the knowns are listed. We're finding the temperature at the cookie, center of the cookie, to determine if it is done. The properties are listed. The equations we need are the Biot number, tau, and then theta naught for wall and theta naught for cylinder. Because you assume it's a short cylinder, you multiply these two together, and from that you can find the temperature at the center of the cookie, which was 177.76. So the cookie was definitely burnt, which makes sense because you put it in for double the time it should have been in. In problem 3, cooling water from Clear Creek is used to condense steam in the Coors factory at a temperature of 28 degrees Celsius. We need to find the mass flow rate of water needed and the rate of condensation of steam. The learning objectives here are heat transfer, mass transfer, and phase change as the steam is condensing. So the log mean temperature is needed because this is a more accurate approximation than just delta T, and then with TLM you can plug that into equation 4 to find the heat transfer there, and then using the heat transfer Q you can find m dot cooling water and m dot steam. The final answers are listed there below.